everyone, my name is Tianjia Zhou, and I'm from the Design Automation Lab of UCLA. I'm very honored to introduce our recent work, Adaptable Analog Cell Library and Automatic AMS Layout, where we try to automatically generate analog layouts by using a digital flow. So a little bit of background information. We all know that physical design today for digital and analog circuits are very different. Digital circuits place and route are fully automated. We have a lot of market-proven, powerful automatic place and route tools that can place and route a million transistors in a very short amount of time. However, analog circuits today still rely on engineers manually placing and routing all the P cells and derive a full custom layout. There's no commercial APR tool and very low flexibility for manual layouts. And the fundamental reason why digital circuits have this automatic place and route capability is because they have standard cells. Standard cells are layout structures for fundamental logic gates, and they're called standard cells because they are standard in that they have uniform height, so they share power and ground rails when they are abutting horizontally. They have uniform width. Their width should be integer multiples of site, where site is usually the contact poly pitch. They have pins on uniformly distributed tracks, and they have uniform place and route granularity called site and pitch. And most important of all, they are abuttable in any directions without causing any DRC or LVS violations. These standardization make it possible for the tool to compactly place the cells into row-based arrays. And if we want to port the digital flow into analog circuits, then we must create standard cells for analog circuits. So this is what previous researchers have come up with when they're trying to create standard cells for single MOS transistors, because this way the flow will have the widest application range. So this is what they did. They take a simplest standard cells, the inverter. We all know that inverter consists of two transistors, one NMOS and one PMOS. So they will remove one transistor by removing the active region or the oxide diffusion in the implanted area to derive the standard cell for NMOS or PMOS. So exemplified here is how to derive a stem cell from an NMOS stem cell from an inverter standard cell, where we can see that the OD region, the active region in the P implanted region is removed, and only the OD in the N implanted region is left here. So this is how a standard cell for NMOS is derived from an inverter standard cell. And there are a few challenges that standard cell as well as the stem cell both face with, because stem cells directly inherited from standard cells by removing half of the active region. The first is that all transistors in standard cells and stem cells use the same L, channel length. This is the reason for that is because the polys will align perfectly when abutted vertically, as shown here. However, this is not quite feasible in analog cases because analog circuits use very short channel length devices as well as very long channel length devices. So in our version of A-cell, which stands for abuttable analog cells, this was actually improved by shortening the gate polys and moving the entire active region upwards or toward the center. So shown here is the shortened gate poly here, and the red part, which is the OD or the active region, is moved toward the center, so that when two A cells abut each other vertically, even if they have different channel length, they will not cause any DRC problems because the gate polys or the ODs will not touch each other. Another challenge that the stem cells face is low area efficiency, because the stem cells derived by truncating the standard cell, so half of the area is almost wasted. And also the maximum allowed finger width is very small, so that a large number of fingers will be needed when engineers try to implement ultra-wide devices. And this is improved in A cells by reshaping the wells as well as the implanted regions in the core part. So shown here, we can see that the N wells is pushed and suppressed, as well as its P implanted areas, so that it will accommodate larger finger widths for NMOS standard cells. But in order to maintain horizontal abutability, we add buffers on the left and right sides, and the buffers mainly consist of W polys as well as N wells and implanted regions that have the same size as standard cells. So this way we can improve the area efficiency at the core, but still maintain horizontal abutability. To better illustrate what abutability will look like for cells with buffers, this is an example of two A cells with buffers will abut each other horizontally. We can see that only the buffers touch and overlap each other, and the core region does not have any overlap uh, or do not touch each other, so that they don't cause any DRC or LVS problems. So in order to qualitatively assess how much area is saved or improved from the A cell, we randomly generate 2,000 sizing parameters and compare the average consumption between the A cell and the same size P cells. We can see that in 28 nanometer, A cells cost roughly 1.3 times more area than directly using the P cells, whereas the stem cells, as shown earlier, will have a relative constant ratio of 2 because half of the area is wasted. And we did this experiment in both a 65 nanometer technology as well as a 28 nanometer technology, and we can see that this ratio is expected to decrease as we scale down towards more advanced technology nodes. There are a few things that we need to clarify before we go next. It seems that A cells waste 30% of more area than P cells. However, this is not really the case because wasted area mainly comes from the procedure of doubling number of fingers to accommodate large finger width. And if the schematic designers are aware of this during the schematic design stage, and they use large number of fingers instead of large finger width to implement ultra-wide transistors, then actually almost no area is wasted. Also, even if a single A cell does waste more area than single P cells, the final layout does not waste. It does not mean that the final layout wastes more area than P cell based final layouts, because first of all, A cells are abuttable regardless of their NP type or their sizings, which a P cell cannot. Also, the powerful placement algorithm for digital APR tools is much more generates much more compact placement than manually placing the P cells. Also, the A cell based subcircuits have more flexible aspect ratios, which makes it easier to put different pieces together. Also, because the whole thing is automatic, so there will be faster and more effective area optimization iterations. Uh, so analog circuits incorporates not just single MOS transistors, but also passive units such as resistors and capacitors. This is rather straightforward to construct an A cell for passive units. So shown here is an example of a crossed-fingered MOM capacitor A cell, which we can see that it has a P cell core, which is CF MOM core, and surrounded with dummy standard cells such as fiddler or tap. So shown here is a P cell CF MOM P cell surrounded by tap cells. And these dummy standard cells construct the legal place and route boundary for the place and route engine to recognize them correctly, as well as to grant them abutability with other A cells, whether they are A cells for MOS or with A cells for caps. And also to provide certain isolation for mismatch sensitive capacitors. These dummy cells can be merged opportunistically when abutting with other passive units. So it seems that a large number of A cells is needed for one PDK because in analog circuits, sizing parameters such as finger width and channel length change continuously rather than discretely in digital circuits. So this implies that a very large number of A cells will be needed for one library. However, this is not quite a big problem because A cells can be generated automatically. A closer look at the A cell will reveal the fact that A cells actually consist of a P cell core, shown here, a P cell core, some redundant complementary layers to maintain abutability with the other A cells, as well as some packaging to standardize the whole cell. So this A cell can be automatically generated. We first start with the same size P cell. We add power ground rails and some complementary redundant layers for abutability. We also add some metal shapes for the pins, and we replicate this small structure for a number of finger times, and we will derive we will derive the core part of an A cell. We then add some buffering structures as well as some power ground rails, and add some VS and label the pins, and then A cell will be automatically generated. So with proper coding, and one A cell would take about 10 seconds to be generated. So even if generating a couple of thousands of cells for one PDK takes less than a couple of hours. So suppose that we already have all the A cells needed, then placing the routing the A cells to derive the final layouts is rather straightforward because the PNR engine will do all the place and route works. So shown here is an example of how a 5 transistor OTA will be placed and routed by the APR tool. We can see that here the 5 transistors will correspond to 5 A cells, and the tool will automatically place and route all the 5 cells into a row-based arrays, and route them properly, as well as add I/O pins here. Each row will have at least one tap cell. The tap cell is responsible for connecting the body parts of the transistors to VDD or VSS, depending on whether they are NMOS or PMOS, and automatically adds filler cells to maintain continuity of the wells, as well as to arrange them into a nice aspect ratio of floor plan. The mismatch sensitive parts in the circuit, such as the differential pair or the differential loads, will be handled hierarchically. So the differential pair and differential loads, such as M4 and M5 or M2 and M3, will be placed and routed first to form one giant macro cell, and the macro cell will be treated as one cell in the next level of hierarchy. So in the second stage of place and route, only 3 cells will actually be placed and routed because some of the cells are placed and routed first in the first hierarchy. The rest of the placements, such as adding filler cells, adding tap cells, adding the I/O ports, are essentially the same as the previous one. So just a brief summary of our proposed flow. The proposed flow has 2 parts. The first part is generating A cells of various sizes, MP types, threshold voltages, and they form a library. And then the second part is handled with the digital APR tool, where the APR engine will automatically place and route based on the gate level Verilog describing the connectivity of the schematic. The engineers or the users will have flexibility or degree of freedom by manipulating with all kinds of constraints such as symmetry, proximity, floor plan, priority, and so on. Okay, so the last we will demonstrate a couple of experimental results. So first is the comparator. We can see the comparator, the sizes are labeled here in the schematic. The comparator has both NMOS, PMOS, and CMOS standard cells, and it also has 2 symmetrical branches. So we will place and route one branch first, where the NMOS, PMOS, and the standard cells will be placed and routed simultaneously, and then we will mirror the place and routed branch to the other half to derive a symmetric layout. We also did a one-time place and route to derive a non-symmetric layout just to demonstrate a symmetry and speed trade-off, because a one-time PNR actually results in a more compact layout, and this would also result in smaller parasitics and faster speed. And a hierarchical PNR will result in a more symmetric layout with smaller input offsets, but larger area consumption as well as larger delays. The next example is a programmable gain amplifier. We will compare the average consumption of a cell-based layout and a manual drawn P cell-based layout. We can see that actually the average consumption is largely the same, but the A cell-based layouts can derive better aspect ratios, and also the large capacitor A cells are actually manually optimized after initial placement, just to demonstrate that engineers can or users can interfere with the place and route procedure at any time. The last case is a 65 nanometer industrial case of a power on reset. We can see that the large array here consists of 144 resistors, which corresponds to our affirmation that the dummy structures of the resistor A cells actually can be merged. We can see that all the resistors here share one dummy standard cell ring, where the inner dummy structures are merged. We also did a comparison between the A cell based layout and a P cell based manual layout. We can see again the area consumption is largely the same, but the A cell based layouts have better aspect ratios and have comparable or roughly the same waveforms. So just some conclusions. In this paper, we proposed A cell, which stands for abutable analog standard cells, and they are the layout structures for single MOS transistors as well as resistors and capacitors. So compared with stem cells, we shorten the gate polys and move the active region toward the centers so that our ASIL can accommodate devices with any channel length. We also reshape the wells and implanted regions to improve the higher area efficiency and add side buffering structures to maintain availability horizontally. Also, our A cell generation is fully automated, so that even if generating a couple of thousand of cells for one PDK takes only a couple of hours. The placement route is automatically done by the digital APR tool. Certain devices or subcircuits can be placed and routed hierarchically to achieve better symmetry or proximity. The experiment part shows that the A cell-based layouts achieves comparable area compared with manually drawn P-cell based layouts, but our layout provides much higher automation and greater flexibility. So this is all for my presentation today. Thank you for your interest, and feel free to email or meet me in the in-person conference. Thank you so much.